So let's consider a situation dealing with an air hockey puck moving across the table. So the puck is initially traveling at 0.6 meters per second, assuming probably after you've hit it. It's traveling towards the other end of the table. There is a resistive force acting on it. We know the mass also. We want to calculate the speed the puck as it reaches the other end of the table. Lots of given information, so let's identify what we know by symbol first of all. So it's initially traveling 0.6 meters per second, so that would mean that VI would be 0.6 meters per second. Let's see, we have a resistive force, F sub R, 0.005 newtons. We know a mass, 23 grams. More than likely, we're going to need that in kilograms. So if we convert that, 1,000 grams equivalent to 1 kilogram. So that's going to give us 0.023 kilograms. Let's see, we want to calculate the speed. So we're looking for VF when it has reached the other end of the table that is 0.55 meters away. So delta X is 0.55 meters. Looking at what we know here, I see VI, VF, and delta X. Those things immediately suggest that we're going to use a motion equation. Motion equation that we can use with those, one of them would be VF squared equals VI squared plus 2A delta X. We would also have enough to use delta X equals 1/2 times VF plus VI times delta T. Now, what we're looking at finding is VF. Well, both of them have a VF in there, but we don't have enough to be able to use either motion equation. So let's consider what else we know in this problem. I've got force and mass. Well, if we have force and mass, that's going to give us enough to be able to use Newton's second law. Net force is equal to mass times acceleration. If we could calculate the acceleration, that would give us enough to use this motion equation to be able to solve down for that final velocity. So then, let's head at it that way. We're going to need a free body diagram. So let me come over here. Here's our air hockey puck. If we draw the forces that are acting on it, field forces, we have the weight. Contact forces, well, there's only one thing in contact with the hockey puck, and that's the surface that it's on. So the surface would be supporting it, normal force. I'm going to assume that the hockey puck is moving to the right. Therefore, the resistive force, which we said was 0.005 newtons, would be acting to the left. There is no forward force. There's nothing that's physically attached that is pushing or pulling on it. Okay, it's gliding basically due to inertia. So this is our free body diagram. The acceleration we want is horizontal. So I'm going to sum all the horizontal forces that are acting on the hockey puck. There's only one. So that's going to be to the left, negative 0.005 newtons is equal to the mass in kilograms, 0.0023, whoops, one extra zero there. How about 0.023 kilograms multiplied by A? When we divide the 0.023 to the other side, we get an acceleration value of negative 0.22 meters per second squared. That negative means it would be to the left based on how we've diagrammed it. Now we've got an acceleration value to plug into our motion equation. So even though I wrote out this one initially, we're not going to end up using that one because we don't need the time, or we don't have the time, we have the acceleration. So we're going to use this top equation. So then when we plug in to find VF, this will be a VF squared is equal to VI, that was given to be 0.6 meters per second, and that quantity is squared, plus 2 times the negative 0.22 meters per second squared, and then multiplied by the delta x, which was 0.55 meters. We're kind of squished in against the edge there. So then when we solve down for VF, that's going to give me a VF value of 0.34 meters per second. Based on how I've diagrammed that, that would be to the right or in the forward direction. So then sometimes when we're analyzing motion, we have to pull several different tools. Always list out what you're given and let it suggest the way you're going to go. We ended up going to motion equations and using Newton's second law to be able to solve down for the quantity we were looking to find. Ponder physics.